Hi, welcome. We are taking a look at Chapter 2, Section 2, the limit of a function. All right, so in general, the idea of limits is talking about the infinite and the infinitesimal, how things work with really, really big numbers and also really, really small numbers. And oftentimes those two things actually end up going hand in hand. The dichotomy paradox, or the racecourse paradox, or quite a few other names, was one of the first kind of ideas that really kind of gave people some headaches. So the idea is, in order to walk to the end of a 128-yard path, you have to first cover half the distance. And then you have to cover half of that remaining distance and half of that remaining distance. As you keep doing that, you keep covering half of things. I mean, now we're down to 2 and 1 and a half and a quarter. We can only get half the distance. All right. Eventually we're at an 8. Well, eventually it's 1 over a really, really large number. But what is that? What happens when you do 1 divided by something really, really, really big? There's still a value to it. And so that's really kind of what has caused some issues. In today's world, we can kind of accept the idea of a limit, that eventually this number is so close to 0, 1 divided by a giant thing, that we can just say the answer to this is 0, and mathematically we can accept that answer. 1 divided by something infinitely large, we can go ahead and just say is 0. All right, technically it's not actually equal to 0, but it is just close enough that we're willing to say, yep, we're good with that idea. All right, so technically the idea is that our value, 0, our limit value, it was close enough once that h value got really, really big that we were able to just say, yes, it is close enough to a certain value, and it's not approaching something else. It's not like it's suddenly going to jump back up to 1 or go negative, that we're good with saying that that answer was 0. All right, and so that leads to this definition of limits. If a function becomes arbitrarily close, all right, arbitrarily means as close as the mathematician or whoever it is doing the problem wants it to be to a unique number L limit as x approaches a value. We do have to say from both sides of A, but not equal to A. Then the limit of f as x approaches A is L. So the limit as x approaches A of some function is equal to our limit. All right, what this means to somebody who is not a math major. In general terms, the limit is what y value does a graph or an equation approach as we get closer and closer and closer to a certain x value. The limit does not mean what is the y when x equals this number, all right, but what are we approaching? Okay, and so generally one of two things happen. It's going to approach a number, and that's great. It's going to approach a value from both sides, both from the left and the right, or it will not approach the same thing. And when that happens, then our limit does not exist. All right, so let me describe this with our graph. We have a graph of a function. Let's step 1, let's just evaluate the function. Now, to evaluate a function, that means x equals 0. When x is equal to 0, that's here. Where is our function? Well, we're at the height of 1. When x equals 3, that is here. Where is our function? Well, I see an open dot there, but here I've got a closed dot. Our function has a value of -1. At f of -2, that means x equals -2. Now I have a choice either up here or down here, and we choose this one, where the dot is. All right, so f of -2 is +2. All right, so that is evaluated function. We find the closed dots. Where is the height of the function? Limits, on the other hand, the idea is what value are you approaching? So as we get closer to 0, from the right side, it looks like this graph's going to 1. As we get closer to 0 from the left side, it looks like it's going to 1. So yes, we would say the limit here is 1. That makes total sense. All right, as x approaches 3, our graph looks like it's supposed to go to this spot as we approach from the left. This side, it looks like we're approaching and we get, again, closer to 0. All right, so the value of the function is down here, but the graph looks like it is supposed to be at 0. So that's why our limit as x approaches 3 is equal to 0. All right, and as x approaches -2 from the left, our graph is getting taller, going up closer and closer to 2. The right side, though, as we get closer to -2, our graph's down here. When those two numbers don't match up, we say our limit does not exist, D and E for short. Okay, so as you can see, the value and the limit don't have to match up. When they do match up, that is great, but kind of sort of boring. So this is what happens most of the time. The value of a function and the value of the limit, usually they match up. All right, but those are just kind of the boring ones. The more exciting and fun ones are like this one, where the limit value and the function value are not equal. All right, or a function value exists, but the limit doesn't. These are the ones, these bottom two, that are usually where we spend our time. The ones where everything just matches, those are just kind of boring, a little lame. We don't spend a whole lot of time doing those. Okay. All right, so when a limit does not exist. So if your graph approaches two different values, one from the left, one from the right, like this one, that's why that limit does not exist. If we approach -1 and we approach 2, the two don't match up, doesn't exist. Sometimes the graph will oscillate, all right, meaning it will kind of bounce back and forth into sine waves. All right, and so if we try to do the limit as x approaches infinity of sine, sine's just bouncing back and forth and back and forth. So it doesn't really have a limit as x approaches infinity. All right. So those are the main two conditions for when a limit does not exist. All right, so besides a graph, how can we evaluate limits? Well, one option is to use a table. Okay, so we're going to try to limit as x approaches 2 of this wonderful equation. All right, I'm going to need a calculator. All right, my computer, unfortunately, had its calculator deactivated, so that's unfortunate. Should have set this up before I recorded, so I apologize. Oh, actually, I think that normal decimals might have been better. No, we'll stick here. All right, so to do our limit, what we want to do is we want to look at values to the left and then also values to the right of +2. All right, so what numbers are to the left of 2? Well, numbers on the left of 2 are like 1.9, 1.99, or 1.999. All right, those numbers are on the left side of +2. Numbers that are to the right side of +2 are like 2.1, 2.01, 2.001. All right, so we want to kind of plug in these numbers that are just a little bit to the left, but really close to +2, but also a little bit to the right and really close to +2. And we want to see what happens. All right, so let's do this. I've got 1.9 squared -4 and 1.9 -2. All right, that value 3.9. All right, so if I pick a number just a little bit closer, like 1.99, we get 3.99. And if we, again, choose even closer to 2, 3.999. All right, so I would say the limit as x approaches 2 on the left side of 2, I would say this value is going to 4. That would be my guess. The right side of 2, as we choose x values that are just a little bit larger than 2, like 2.1. All right, I've got 4.1. If I choose something closer than 2.1, like 2.01, we get 4.01. and 4.001. So again, these numbers are getting very, very, very close to 4. All right, great. So I feel like the limit of this function is, in fact, 4. Now, if I try to just plug in 2 exactly how we see it, notice it does say that the graph is undefined. Okay. Now, a problem like this is going to be kind of sort of like this one, where both the left side and the right side are going to the same number, but the actual function itself didn't quite match up to that. This function is undefined. There would be a hole in this graph, but there wouldn't be another little dot right here. This function is just undefined when x equals 2, but the limit as x approaches 2 is equal to 4. All right, we can try 1 or 2 more of those and see how we do. All right, so for number 2, the limit as x approaches 4 of the square root of x minus 2 over the square root of, over just x minus 4. All right, so again, let's just try that to actually just step 1. What happens if we just try to plug in 4? Okay, the square root of 4 minus 2 over 4 minus 4. Notice it is undefined. Okay, so something interesting is happening when x is equal to 4. And that made sense. We can't put 4 in here. We can't do 4 minus 4 is 0. We can't divide an equation by 0. So that's why a limit in this situation is kind of something we want to know about. So we need to choose numbers that are to the left and right of 4. So what is just a little to the left, a little smaller than 4? Well, 3.9. 3.99 and 3.999. These numbers are just a little bit to the left of 4. So instead of actually plugging in 4, we have to plug in numbers just a little bit smaller. All right, so we've got 0.25. If we do 3.99, again 0.25. And again, 0.25. Looks like those are all going right to about 0.25. And I think if I just add a few more 9s in here, notice again, it's just getting closer, really close to 0.25, all those extra zeros. All right, some numbers just a little bit to the right of 4. Uh, 0.248, 0.25, 0.25, and 0.25. I feel okay jumping the gun on that one. All right, so again, same idea. Both numbers are going to 0.25, so our limit is 0.25 a quarter. Okay, we couldn't actually plug in 4, but we do have the value of a limit, and that is what the deal is. All right, so here's sine of 1 over x. If I just try to plug in 0, it'd be 5 sine of 1 divided by 0. I can't do 1 divided by 0, so I can't just plug in that number. So again, this is kind of the point of limits. They let us evaluate things, or at least have an idea of what a function does as we get closer and closer to values. All right, so 5 sine of 1 over, now I need to probably be in radian mode. 90% of the things we do should be in radian mode. I say it specifically here, but I forgot to say that up here. So we want to put some numbers that are just a little to the left. So a little bit to the left of 0 are negatives. All right. So 2.7. 2.5. That one's weird, negative 4.1. So the first two were making sense. The third one, not so much. If I try again, if I put another 0, 1.5, try again, negative 1.7. These are just bouncing all over the place. All right, they're not getting closer and closer to a number. They just keep getting weird. All right, if we do the same thing, but to the right side, so 0.1, 0.01, 0.001, these numbers are just a little bit bigger. Negative 2.7. Negative 2.5. And positive 4.1. Well, again, weird numbers that are not getting closer to the same thing. They're kind of bouncing around. All right. Now, a graph of Desmos should actually help explain this. Take a look at what happens to this graph as we get close to 0. Look at this mess of an equation. The sine wave is just going to keep bouncing up and down, up and down, up and down, up and down, and it just becomes this absolute mess right around 0. All right, because as you do 1 divided by really small, you get a really big number. And sine, as you put in really big numbers, just keeps bouncing. We talked about that. And so that's the general idea. This graph, this limit, does not exist. All right, so that's good. All right, and we can do this with sine of theta over theta. So sine of x over x. Let's do this one graphically. I hope that's okay. We're doing this as theta approaches 0, so as x approaches 0. Let's take a look. Well, as we approach from the left, look at the values of y as we get closer and closer to 0. It looks like we're getting pretty close to 1. But when you're actually at an x value of 0, notice we get that 0 undefined spot. On the right side, as we get closer to 0 from the right, so from the right moving to the left, again, it looks like it gets pretty much equal to 1. Undefined at 0, but we're a y value of 1 as we're close by. All right, so the limit as we do this is 1. All right, so that's the general idea that we're working with. We can do this with tables. Desmos does a great job with graphs. All right, tables are a little bit better, especially for certain ones. Graphs are great visuals, but they're not reliable mathematic ideas. That's not the right way to say that. They're very reliable mathematical ideas, but they're not showing your work. All right, you can't just say the limit is 1 because of the graph. All right, we don't want to do that, especially when I say solve it using a table. So sometimes we want to just do the algebra of things. And graphs, they're great visuals, but they're not algebra. All right. So usually we do want these tables, like on your test or on your projects. I will expect to see a table if I ask for a table. Okay, you can't just say it's 1 because of the graph. Don't do that. All right, one-sided limits. If you notice a little minus sign after the number, or a little plus sign after the number, that means talking about just from the right or just from the left. Okay, so we have that same graph from before. The limit as x approaches positive 3 from the left. We only look from the left side. So the graph is approaching a height of 0 as we approach it from the left. As we approach it from the right, still 3, but from the right, yeah, that's also 0. So that's good. So we can kind of like break the limit apart into two smaller things, just from the left and just from the right. So like a table, that would be like just the smaller numbers or just the bigger numbers. We don't have to do both. Okay. X approaches negative 2 from the left. That limit is 2. As we approach negative 2 from the right, that is negative 1. So those two numbers don't match, so the overall limit does not exist, but each individual limit does. Okay? And we can do this with piecewise functions. Okay, so we have this piecewise function in algebraic form. Evaluate the following limits. So letter A says as we approach 2, but from the left. Okay, a little negative. So I want to put in my table, really the only choice I have is a table. I want to put these three numbers. 3 numbers is usually good to put into our table. All right, so my equation on the left, if x is smaller than 2, these numbers are smaller than 2, I would only use the top equation. Okay, as x values are smaller than 2, I only use that top equation. So 1.9 plus 1 is 2.9. 1.99 plus 1, 1.999 plus 1. So it looks like these are going to 3. Letter B, the limit as x approaches 2 from the right. So I want things like 2.1, 2.01, 2.001. All right, from the right, x value is bigger than 2. Piecewise function, that means I only use this bottom equation. All right, so I might need to use my calculator for that one. So I need to do 2.1 squared minus 4. .001 squared minus 4. 2.001 squared minus 4. All right, let's say these numbers are going to 0. So the limit on the left approaches 3. The limit on the right approaches 0. We can find those two individually, but if I'm ever asked just the limit as x approaches 2, not from the left, not from the right, so both of this function, this would not exist. When those two numbers don't match, overall our limit doesn't exist. We can find each individually, all right, but if we put them together, this would not exist. All right, infinite limits are a wonderful, fun time. All right, one-sided limits can have a result of positive or negative infinity. Okay, and that's fine. That can happen. So as we approach 2 from the right, so 2.1, 2.01, 2.001. If we look at our Desmos, doing 1 over x minus 2. I've got 10. 100. 1,000. So I hope you're with me. This limit is going to get really, really big. All right. The limit as x approaches 2 from the right can have a value of infinity. All right. We can say that the limit approaches infinity. If we do this from the left, so if these numbers are what, 1.9, 1.99, all right, I've got negative 10, negative 100, and negative 1,000. So that would be negative infinity. So overall, we would say our limit does not exist if we compare both of them. But each individual one can say they go from, like, this one goes to positive infinity, this one goes to negative infinity. A left bound limit or a right bound limit, or left-sided limit or a right-sided limit could have positive or negative infinity as your answer. If you look at both of them, all right, the limit would not exist. All right, so for instance, let's take a look at a graph. We've got 1 over x minus 2 squared. All right, taking a look at that graph, as we approach 2, you see how both arrows go up in this one. So the limit from the left is positive infinity, and the limit from the right is positive infinity. So our limit overall would be positive infinity, right? If they both equal positive infinity, then yes, our limit can be infinite. If they are positive infinity and negative infinity, then no, we don't say that our limit is to infinity. It would not exist. Okay, so it's just kind of a notation thing on when it can be positive or negative infinity. All right, so one quick check of practice. Maybe pause the video, try to do these 4 problems on your own using that graph, and see what you can do. See if you can do them. 5. So pause the graph or pause the video. And I'm going to answer this in 5, 4, 3, 2, 1. All right, so the limit as x approaches negative 4 from the left, let's say 3. As we approach negative 4 from the right, I can do this. Negative 4 is here from the left. That has a height of 0. From the right, that has a height of 0. Overall would then be 0 since they match. All right, and evaluate the function at negative 4. Well, that is also 0. That is fantastic. All right, letter B. At negative 2 from the left, that is 3. From the right, that is 3. Overall, yep, those match. That's 3. But our function at negative 2 is undefined. We wouldn't say doesn't exist. Doesn't exist is for limits. Undefined is for functions. All right, letter C. As we approach 1 from the left, let's say that's going to 6. From the right, that's 3. Those two numbers don't match, so our limit does not exist overall. And the function itself is defined. Yes, I have a dot at 6. So sometimes these things can not match, and that is still correct. All right, letter D. 3 from the left, that's negative infinity. 3 from the right, negative infinity. So yes, overall, negative infinity. But what is the value of the function itself? Well, that's undefined. Okay, so hopefully that made sense for these different possibilities, how we can do limits with a graph and how we can do them with a table. Hope it all made sense overall. Reach out if it doesn't, please.